statistical speech, but we're going to do it much more thoroughly now. If you have taken statistics before, some of it might be familiar to you, some of it might not. Even if it is familiar, it's very useful to get a refresh. How many of you have seen Bayes' equation before? Bayes' formula? I was hoping all the hands would go up. How many of you are able to derive it right now on the board? Okay, well, you took my class and I asked the same question there. At the end of either this lecture or next one, whenever we get to Bayes' formula, you will be able to derive it yourself in your sleep with your head tied behind your back, and it's really, really easy. Once you really understand what it's about, it should be very, very easy. Okay, so we're going to start with a revision of what random variables are. So a random variable is a variable that can take on different values with different probabilities. So it should take on at least two values, could be many more, could be infinite number of values, and there's typically a probability distribution associated with that random variable that tells you each value with what probability it might take it. I will denote random variables with green. I don't think we'll need much of this. I'm going to start here. So x would be a random variable, also known as RV, and I will use green for it. Now, if I write, I'll start with white and then I'll go over the color. If I write big X equals little x, what is this? This is not a mathematical equality, this is an event. It's describing the event that the random variable big X took on a specific value small x. Or similarly, I could write big X took on the value 3. Or big X took on the value ABC. Whatever values the random variable takes, it could be numerical, it could be characters, it could be anything. But when I write things like this, on the left side is a name of a random variable, an uppercase letter, and on the right hand side is some either specific literal value or some kind of another variable. This describes an event. You can think about it as an event in information theory if you remember the tutorial. Now when I write the probability of big X taking on some value small x, this is the probability of this event. And sometimes, for short, I may write it as P of X, P of small x. This is how you may see a lot of things you may have seen before, a lot of probability expressions. But whenever you talk about a probability, it's a probability of an event. And whenever there's an event, there's an underlying random variable that takes on a particular value or set of values. So this is just shorthand for this. But keep in mind that there's always a random variable that takes on this value. And usually it will be clear which random variable it is. Now is a good time to review some rules of probability theory. So, P of X and Y. So this is shorthand for probability of the event that random variable big X took on the value small x and random variable big Y took on the value small y. Okay? P of X and Y, which we sometimes write as P of X comma Y. So that's another shorthand. When you write a joint probability of several events, you're implying it's an AND of the intersection of all the events. And we can write it down using the chain rule as P of X times P of y given x. Alternatively, we can write it as P of y given P of x given y. Both of these are using the chain rule. You could use it here or you could use it there. And if you have more than two events, x, y, and z, you can use the chain rule in any order. P of x times P of y given x times P of z given x and y, or P of z times P of x given z times P of y given x and z. You can apply the chain rule in any order you want, but you have to make sure to condition at any one point on all the events that were already predicted. So in the general case, P of x1 through xn can be written down as P of x7 times P of x, favorite number, 2 given x7 times P of, at some point, x3 given all the, we had x5, x7, everything else. You get the idea. This is the chain rule. Chain rule does not have to go left to right or right to left. It can go in any order. Okay, one more refresher rule. Theorem of total probability. Take the case where some random variable A can take on values A1, A2 through AN. These are mutually exclusive values. And there's some other random variable B that takes on some other values. Then the probability of small b, which I could write as big B equals small b, or I can just write P of small b, that's my shorthand, can be broken down into a sum of probability of B given AI times probability of AI. I goes from 1 to n. This is n here. This can also be written as probability of AI and B. So from here to here I use the chain rule. Right? I do first P of AI, which is here, and then P of B given AI. There's a very nice picture that goes with this. This is A1, A2, all the way through AN. This is a partition of the space of events into all the possible AIs. Right, the AIs form a partition. They're mutually exclusive. That means they don't overlap. And together they cover the entire space. Together they cover the entire space means that sum of P of AI is 1. Right, that's what the partition means. I deliberately made some of them fat and some of them thin because the probability of the AIs are not all the same. Now comes B, a particular value of B, and I can draw it here. I could have also drawn straight lines, but the important thing is that the lines are not cutting in the same place in the AIs. So for some AIs, for example for A sub n, probability of B could be quite large, whereas for others, like A3, probability of B given A3 could be quite small. And now the interpretation is P of AI is the size of this slab. P of B given AI is the fraction of this slab that is taken by B. So together, the product of these two gives you the absolute area of the marked area. absolute, namely relative to the whole thing being 1. You can see that as in this form, the joint probability of A, I, and B is this particular area, and for a different I it's this area, and so forth. When you sum over all these areas, you get a total shaded area. The total shaded area can also be thought of the overall probability of B. Okay, so much for a review of probability. Any questions so far? Okay, let's go back to random variables. And I'll use green here. Here's a very important property of random variables. Any function of a random variable is also a random variable. What does a function of a random variable mean? Suppose I took x and added 3 to it, assuming x is a random variable over numbers. So the new entity, x plus 3, can also be thought of as a random variable. It takes on different values with different probabilities. Whatever probability x had of taking on the value 1 is the same probability that this new random variable has of taking on the value 4. Okay, so it just shifts the set of values, but the underlying distribution remains the same, kind of, in this case. Or if I have two random variables, x and y, I can say x plus y, that's a new random variable. And I can get arbitrarily complicated. I can do sine of 3x minus 2y squared. That's a random variable. So it actually should be in green. What does it mean that it's a random variable? It means that not only do we not know the value, but intrinsically there is no one value. There's a distribution of values. Now, once you perform an experiment and you have concrete data, you no longer have the distribution of values, you have a specific value. But before you perform the experiment, you think about all possible worlds. The way to think about random variables is what's associated with them is not a value, but a distribution of values. And if you take a function of a random variable, what's associated with that is also a distribution of values. Questions so far? Comments? Okay. Now, how is all this related to machine learning? We have a hypothesis space which contains many hypotheses, which we usually call little h. Many times, all the hypotheses in the hypothesis space can be parameterized by one or more parameters. That means the hypothesis space can be described as a family where every member is characterized by a particular value of a parameter. An example would be if your hypothesis space is all Gaussians, then they can be parameterized by two parameters, the mean of the Gaussian and the standard deviation of the Gaussian. If for some reason you started with a hypothesis space that is only Gaussian with a standard deviation of 1, then you have only a single parameter, the mean. So sometimes the hypothesis space can be characterized by parameters. Other times it has this weird structure like decision trees, which is not easily characterized by parameters, but conceptually you can think about it as also being characterized by a set of numbers, parameters. The parameters may not be continuous, but they're still parameters. Statisticians like to use theta for parameters. You can think of theta as a single parameter, or statisticians sometimes use it very generally to describe any set of parameters. Sometimes they will be didactic and will put a bar on top of it to remind you that it's an array of parameters, a vector of parameters. Sometimes they won't even bother with that. So you can interchangeably think of theta as being a single number or a set of numbers. So choosing h from the big H is kind of the same as choosing the parameter. Theta. Keeping in mind that theta sometimes has more than one parameter. It could be mean and a standard deviation, or it could be 10 parameters, or it could be even a very large number of parameters. choosing a parameter theta is known in statistics theory as statistical estimation. We dealt with it a little bit when we talked in chapter 5 about estimating errors. The random variable, if you remember, was some measure from the data of the errors, like the test set error, and the underlying parameters was a true error. And we talked about how the measure from the data can fluctuate around the true error, and what can we say about how close it is, or right? So this is all the same theory, statistical estimation. Statistical estimation you can think of as breaking into several different parts. There's point estimation, when you're asked to give back as an answer a specific theta, specific value, call it theta star. This is kind of the same as having to choose a single hypothesis as your answer. Another form of statistical estimation is coming out with a confidence interval, right? You can only do that if your parameters are continuous, if there's some sense in which some thetas are closer, if there's a measure of distance between the parameters. So it won't always be a parallel here. If your hypothesis space is parameterized by things that are either continuous or live in some kind of Cartesian space, or in some kind of space that has a metric on it, then there would be an equivalent here where you choose maybe a version space, some kind of a version space that contains only hypotheses that are close to the correct one. If your hypothesis space is highly structured, like decision trees, it may be hard to find an analogy there. But generally, I want you to think of H and theta as kind of the same thing. Most of the time they're the same thing. They are parameters. The thing about parameters that sets them apart from random variables is that they are fixed in some sense. They're unknown, but they don't vary with the data. They were in a way fixed before the data was created, fixed before the experiment was done. Because they're fixed, I'm going to draw them in red. So H and theta are going to be red. Think of red as fixed but usually unknown. Think of green as not fixed, but actually representing a whole distribution, whole set of possibilities. We're going to talk a little bit about Bayesian statistics and non-Bayesian statistics, and Bayesian statisticians tend to blur the distinction between green and red. We'll talk about it very soon, but for now, think about these as two different creatures, green and red. Okay, so if our job is to choose a single hypothesis, that means we're looking to do point estimation, find a single theta. What would be an example? Our favorite example is the flip of a coin. You have a coin, you would like to know the probability of head. Probability of head of a coin is what, green or red? It's red. It's a parameter. We don't know what it is, but it's fixed. Once we have the coin, that value, the true probability of head, is fixed. It was determined when the coin was made in a factory. Maybe different coins have different values, but the one particular coin we have in our hand is a fixed red parameter, probability of head. Now we don't know that value. So example would be coin. And theta is going to be probability of head. We know that theta is in a particular range. In our case, it's in the range of 0 to 1. But that's all we know about it. You could argue you know more, but for now, all we agree on is that it's some number between 0 and 1. It's a fixed number. Now we contemplate an experiment to help us determine that number. What would be the experiment? Taking that coin and flipping it 10 times, 100 times, any number of times. The result of the experiment is a sequence of tails and heads. Let's say 10. Let's say we decided to flip it 10 times. So the result of the experiment is a sequence of 10 H or T. So let's write a variable that tells us that the nodes x1, x2, x10, where each one of these could be tail, head, tail, tail, or any other combination. So x here is an array of 10 values. In fact, let me change that. This would be big X1. This is big X2. So there are actually 10 random variables here, each taking on the value head or tail. What color are they going to be? Green, right? This is green, and these are green. They're green because we cannot decide in advance what value they'll have. We know that they can take on, each one of them can take on two values, T and H. We don't actually know with which probability. We know that it's with probability theta, but we don't know what theta is. Now remember what we said about any function of a random variable is also a random variable. So one function we can take of these 10 x's is we can take their average. One over 10 sum xi. I goes from 1 to 10. What color should this be? That's green. This whole thing is green. I'll give it a name. Well, I already used bar here for an array, and that's not good. Let me just call it average. Yeah, I'll call it average of the axis. So this is all green. This whole thing is green. I don't know. Why is it green? Because it's a random variable. The average, I'm sorry, when I say average I should have defined clearly. It's the average number of heads. Okay, so I associated head with 1, with the number 1, and tail with the number 0. This is not a trivial thing. I should have told you that that's what I'm doing. But you kind of figured it out on your own. I'm just interested in counting the number of heads. So the random variable that I defined, x3, takes on the value 1 or 0 based on whether the result of the third flip is a head or a tail. Now I can talk about averaging them. The average is the fraction of the 10 tosses that are 1, right? It's a random variable in the sense that I don't know in advance what value it would take. What values can it take? Sorry? How many values can it take? Almost? 11. 0, 1 over 10, 2 over 10, 3 over 10, all the way to 10 over 10. 11 values equally spaced between 0 and 1 inclusive. Now, can you tell me what is the probability that it would take on the value 3 over 10? Let me call this some other name. Call it Z. Z. So what is the probability of Z equals 0.3? Can somebody tell me? Tom? It's a binomial distribution, so it's 10 choose 3 theta, which I don't know. This I guess should be theta to the 3 and 1 minus theta to the 7. So it's some function of the red. If I knew the red, I could tell you exactly. This is something we often do. We pretend that we know the value of the parameters of the red just to write down the way the random variable is distributed. But if we don't know it, we don't really know the distribution of the random variable. We know the general shape of it, but we don't know the actual number because we can't plug in the red. Okay, why did I create Z? Because I think it's a pretty good way of estimating theta. Do you agree with me that Z, the average number of heads, is a decent estimator of the true probability of head? Z estimates theta. What does it mean that Z estimates theta? Theta is fixed, it doesn't change. Z is green. On different days it will take different values. But still, we think it's a good estimator. Do we? I mean, do you agree with me? If you disagree, please speak up. If you were tasked with figuring out the probability of head, figuring out the value of theta, and all you had access to was a list of 10 tosses, what would you do? See? What do you mean by frequency?
Number of heads versus number of heads.
Number of heads, which is the same as taking the average, right? So you will do the same thing I do. Somebody else do something else? Now, why would you use the frequency or Z? Why do you think it's a good estimator?
This is the frequency that the expected value of Z is theta.
That's a very good observation. What you're saying is that Z will not always give us the correct answer, but on average it seems to be just right around the same place. So sometimes it will overshoot the right answer, sometimes it will undershoot it. So, in fact, let's start with the simpler thing. Z, there are times when Z is guaranteed to not give you the right answer. For example, if the probability of head is not an exact number of tens, if it's 0.35, then that's a good one. I thought it was a ringtone. Oh, that's cute. It's a talking brain. Does something trigger it? It's like a blend that swallows everything around it. Okay. So, choosing Z as your estimator does not guarantee that you'll get the right answer. In fact, there are situations where you're guaranteed to never get the right answer, such as when the probability of head is 0.35 or 0.32 or 0.37. You're guaranteed not to get the right answer. So what kind of a method is that? But it has some advantages. Okay? You can choose other methods of estimating theta. So let's talk a little bit about that. Z is an estimator. Z is a function of the data. It's green, which means it gets on different values at different times. So it's not a number. It's a function or a recipe that on different days would give you different numbers. So Z is an estimator. An estimator is a green beast. It's a function of the data, so it's a random variable. An estimator is a random variable. But it's a random variable that was selected especially to try to estimate something, like the value of the parameters. Now there can be many different estimators, and they would yield different answers at different times. And you can't choose after the fact which estimator was better. You have to choose ahead of time which estimator you're going to use, because you don't really know the true value of data. So what properties are useful in an estimator? So think about all possible estimators as all possible functions of the data. What are good properties for an estimator to have? Ben?
Well, for example, here we know that if we go to infinity with the number of trials, the estimator will tend to the real problem. This would be a good problem.
Very good property. You want your estimator to be such that as you get more and more data, it becomes better and better in some sense. Maybe it's guaranteed that as you get the amount of data goes to infinity, it settles on the right answer. So it should be asymptotically consistent. That would be a good way to describe it. So that's one good property to have. Please?
And it converges quickly, so it has a low variance.
It should converge quickly. Hopefully to the right answer. Hopefully to the right answer. Because you can imagine an estimator converging very quickly, but not to the right answer. Okay, that's good. You guys are ahead of me. I wanted to start with something a little simpler. The first thing it should be is kind of fair, in the sense that it should not tend to undershoot any more than it overshoots. Okay? If you have an estimator that's consistently, or not consistently, but it tends to underestimate the answer, that's not great. If it tends to overestimate the answer, that's not great either. You understand that it's going to make mistakes, but at least you want those mistakes to be balanced on average. Should overshoot as much as it undershoots, kind of. Okay, that would be one property to start with. We'll come back to both of your properties. So let's put it here. Desired properties for an estimator. Let me give you one more piece of notation. If you're trying to estimate a parameter theta, typically statisticians would write the estimator as theta with a bar on top of it, or theta with a squiggle on top of it. I'll use squiggle. So theta with a squiggle, and to remind us this is a function of theta, I'll write it like this. So desired properties for an estimator, theta squiggle of the parameter theta, green and red. So the first property I wanted to discuss is something like fairness or balance. Another way of saying it is it should be correct on average. When I say average here, I mean averaging over many days, many different scenarios. Same coin, you flip it 10 times, you get the result, you apply the estimator function that you chose, you get a number. You flip the coin another 10 times, you apply the same estimator again, you get a different number. You flip it another 10 times, and another and another and another. Average over all these sets of experiments, I want it to be correct on average, which is another way of saying that it should overshoot as much as it undershoots. Okay? So, if you talk about averaging the performance of an estimator, that means taking an expectation. And the expectation is over the set of all possible experiments, or all days, or all worlds. So that would mean the expected value of the estimator should be equal to what? The true parameter, red. Ideally, for the estimator to be correct on average, and remember, whenever it's green, it means it has a dependence on the data. What is the expectation over? That's very important to understand. The expectation is over all possible data outcomes. Another way of thinking about it is you can simulate it by every day running the experiment again and getting some new different data. Now something happens to green when you apply expectation to it. You know what happens to green when you apply expectation to it? It becomes red. It becomes fixed. Because when you apply expectation to a distribution, you get a single number. It doesn't necessarily become red in the sense of it's a parameter that's unknown, although often it would be. But the important thing is it's no longer green. Green means a distribution. Red is a single number. You apply expectation to green, it's no longer a distribution, it's a single number. So this thing, and that's important because otherwise we'd have some strange undefined thing here, green equal red, which doesn't make sense. You cannot compare a distribution to a single number. But here we took expectation of it, this became red, and then... Now this may not always be true for all estimators. For some estimators it's true, for others it's not. For estimators, when it is true, the estimator is called an unbiased estimator. So an unbiased is trying to capture the same thing I said as fair or balanced or correct on average. In the more general case, there may be a bias, and the bias is defined as the expectation of the estimator minus the true value. And I'll put the colors now. So this is red, and this is red, even though this is green. So you have red minus red, that means this is red also. Red just in the sense that it's a fixed number. We may not know what it is, but it is a fixed number. That's what red means. So we would prefer an estimator that's unbiased, namely that has a bias of 0, but we might settle for an estimator that has a small bias. We don't want an estimator that has a large bias. Okay, is that Kim? Back to your suggestion. You wanted an estimator that doesn't fluctuate too much. Okay? Let's forget for a moment about doesn't fluctuate around what. You just don't want an estimator that some days will give you this answer and another day will give you a way off answer. Yes, granted, the data changes from day to day. But if you have enough data, you want the estimator to not change too much. Okay? So this is captured by the variance of the estimator. So we want an estimator with as low a variance as possible. So let's write the second property here. Property number 2. Low variance. When you talk about a variance of a distribution, the definition of a variance of a distribution is the average square difference between the value that varies and its mean. So the value that varies is theta squiggle, the estimator. To remind you, it's a function of the data. Just by drawing it in green, you should know that it's a function of the data. By definition, it's a random variable, that means it's a function of the data. Now I want to take the square difference between this and the expected value of this thing. Now if I want to apply this in colors, this would be green. Taking the expectation would turn this whole thing into red. So it's a constant, it's a number, it's not a distribution. Now I take green minus red. Is that allowed? Can I do green minus red?
Yes.
Yes, I can. Remember, I can do x plus 3 or x minus 3. X is green as a random variable, and x minus 3 is also a random variable. So here I take the random variable and I subtract some constant from it. So what is this whole thing? What color?
Green.
Green. The whole thing is green. Thank you. So I'll put it in green parentheses. I'm going to square it. What does it become now? Still green. So now I have the squared difference between the value of the random variable and its mean. And that's a random variable. I'm going to take its expectation. What does it become now? Red. Taking expectation of green turns it into red. And this is called a variance. So now I have two, I don't know why I called it B here, I should call it bias, it's a full word. So I have bias, which is a red, a constant number, maybe not known, that characterizes an estimator, and I have a variance that characterizes an estimator. Different estimators may have different biases and different variances. Now, back to the feedback I gave you. It's good for an estimator to not fluctuate too much. But really, we want it to fluctuate very little around the right value. Right? It's very easy to come up with an estimator that doesn't fluctuate at all if you don't care about anything else. Can you think of an estimator of probability of head that has no variance? Zero variance, it's ideal. Please.
0.5.
Thank you. Excellent. 0.5 is a constant. Technically speaking, you can think of it as a function of the data, but really it doesn't depend on the data. It always gives you 0.5 no matter what the data is. What is the mean of this estimator? 0.5. And it's always the same value, so its mean is 0.5. What is the variance of this estimator? 0. Can you think of another estimator that has zero variance? 0.6? Yeah, can you think of others? 0.7, 0.3? Any fixed number, any constant can be thought of as an estimator that is sort of nominally a function of the data, whereas we all know it doesn't really depend on the data, but you can think of it as a function of the data that basically throws the data away, ignores it, and just gives the same answer all the time. That has zero variance, but you would agree it's not a great estimator because it has nothing to do with the truth. So what we want is small fluctuations around the correct value. The way we're going to try to capture it is with something very similar to the variance. It's going to be the mean of the squared difference. But instead of squared difference between the estimator and its mean, it's going to be the squared difference between the estimator and the true value. Okay? This criterion is called mean squared error. So what we want is low mean squared error, MSE. How are we going to define the mean squared error? Very similar to this, but there's a slight difference. We're going to start with the estimator itself, it's green, and subtract from it the true theta. That's the error. square it, you got the squared error. So we're going to work backwards from the definition. Error is this part. Squared error is with a square. Mean means taking the expectation of this whole thing. Now let's put some colors in. What color are the parentheses? Green. What color is the square? Green. What color is the E? Red. So this is MSE, defined this way. MSE seems to capture both our desire to be near the correct answer and also to not fluctuate too much. Okay? Now let me show you one of the nicest fundamental results from statistical estimation. And it's just a little bit of algebra. And I'll do it where there's a lot of light. And I'm not going to use my colors. It's going to be too cumbersome. I'm going to start with the MSE. E of theta. Now, because I don't use colors, you have to be careful when I put a squiggle there or when I don't. That's important. With a squiggle is red, without it with a squiggle is green, without it it's red. Theta minus the real theta squared. I'm going to write it as E of, I'm going to open the parentheses here and close them there, squared. So far nothing changed. We're going to take the part inside and manipulate it a little bit. I'm going to start with theta squiggle, and now I'm going to add and subtract the expectation of the estimator, E of theta. Actually, I'm going to subtract first. Subtract E of theta, theta squiggle, and add E of theta squiggle, and here is minus theta. So I just took this and opened it up. Now, call this A and call this B. What you have here is the expectation of A plus B squared. Now I'm going to use algebra and use my formula for A plus B squared. It's A squared plus B squared plus 2AB. This equals the expectation of, I'll just write it, A squared plus B squared plus 2 times A times B. Expectation is a linear operator, which means the expectation of 3x is the same as 3 times the expectation of x. And the expectation of x plus y is the same as expectation of x plus expectation of y. And the expectation of x times y is the expectation of x times the expectation of y? No. No. You can't put a linear operator into a product. You can put it into a sum, but not into a product of random variables. Okay? I was hoping you would catch me there. So, E of 3x is the same as 3 times E of x. And E of x and x plus y is the same as E of x plus E of y. I'm ignoring the squared brackets. But E of x times y in general is not E of x times E of y. Although if x and y are independent, then it is true. But here all I have to do is apply a linear operation, so I'm going to do E of A squared plus E of B squared plus 2 times E of A times E of B. I'm sorry, not true. 2 times E of A times B. But actually it will be true in a second. Okay. Now let's see what E of A squared is. A squared is the difference between the estimator and its mean. So estimator minus its mean squared, The expectation of that, what is that? That's the variance. B is the expectation minus the true value. Do you see this defined anywhere on the board? The expectation of the estimator minus the true value. Bias. Okay? Now, this has to be squared. But bias is red. Bias has no green left in it. This applies to this, turns it into red, and this was red in the first place. So when you apply an expectation to something red, it's a no-op. Expectation of a constant, an expectation of a number is just the same number. You can apply expectation as many times as you want to it. Right? So expectation of the bias squared is basically the bias squared. Bias squared. Let me put some color here. This is red. This is red. This is red. And this is green. This is green. This is green. Okay. Now I have another component here. And it's 2 times E of AB. Now I found out that B is actually red, whereas A is green. Right? B is red because it's red minus red. A is green minus red, so it's still green. But because B is red, it's a constant, it falls in this category. It's the role of 3. I can take it out of an expectation. The only times I'm stuck with the expectation of a product is when both components of the product are green. Right? So I can take B out. So it's 2 times B, which is bias, times the expectation of A. Now expectation of A is expectation of a difference. Something like M minus N. E of this minus this is the same as E of this minus E of that. Okay? E of this is the expectation of the estimator. What is the expectation of the expectation of the estimator? The expectation of the estimator is the expectation of the expectation of the estimator. The expectation is this. If you apply expectation once, applying it again does not make any difference. By the way, what do you call an operator that applying it once is the same as applying it any number of times? Idempotent. An idempotent operator, once you apply it once, applying it subsequent times does not change the value. An expectation, the same expectation over the same distribution, is an idempotent operation. So when I apply this to this, I get the same thing as here, and when I apply this to this, it stays the same, so this is 0. So I can cross this out. So I'm left with MSE, the mean squared error, is equal to the mean squared error of an estimator, which is a red, it's a number that's associated with the estimator, is equal to the variance of the estimator plus the square of the bias of the estimator. Very fundamental result in statistical estimation. And now we're free to choose different estimators, and we can say we want to minimize the MSE. We don't have to, we can minimize something else, or we can optimize something else. But a very common thing we might want to do is find an estimator that minimizes the MSE. And sometimes you would have a trade-off between estimators that minimize the variance but maximize the bias, or minimize the bias and maximize the variance. Often what you do is you consider estimators that are unbiased, they have 0 bias. And then among those you try to find the one that has the lowest variance. But there are situations where the lowest MSE estimator is actually not an unbiased one. Sometimes it makes sense, if what you care about is the mean squared error, to pay with a little bit of bias. you will know that the estimator will tend to overshoot. On average, overshoot more than undershoot. But the MSE would be better. And there could be other criteria, such as, then was it your suggestion? Yes, that asymptotically you should have the right answer. If the estimator is unbiased, then you're guaranteed to have the right answer. Well, if it's unbiased and the variance goes down with the amount of data, then you're guaranteed to asymptotically go to the right answer. But even estimators that are biased, if the bias gets smaller and smaller with the amount of data, then asymptotically you'll be fine. Here's an example. Think of an estimator for flipping a coin, for estimated probability of head, that pretends that there was another flip of the coin that landed on head. So it pads the answer with one more head. So if you had 10 flips and you got 3 heads, instead of giving 3 out of 10, you get 4 out of 11. Is this estimator biased? Yes, it is biased. It is biased high. But the bias shrinks towards 0 as n, the number of flips, grows. So asymptotically, that bias doesn't matter. You can also think of the opposite kind of bias, the one that shoots low, the one that pretends that there was one flip that said there was tail. So if you got 3 out of 10, the answer would be 3 out of 11, as if there were 3 heads out of 11 tosses. That also has a bias. It's a negative bias. It tends to shoot low, but again, asymptotically, it wouldn't matter. Now, the 3 out of 10 estimator, the one that we defined as Z there, is unbiased. I can prove that to you. We can actually calculate its expectation and sum over all possible values, and we will get the right answer. You can actually prove that the estimator is unbiased. Can you think of another estimator, in the case of flipping 10 coins, that is also unbiased, but it has a higher variance?
Throw away some random data.
Throw away part of the data. Consider only every second flip. So even though you toss the coin 10 times, you only look at the 2nd, 4th, 6th, 8th, and 10 result and average those. It's unbiased, right? You can say it's fair. It doesn't favor head versus tail. It's fair, but it has a higher variance because it's based on less data. It is somewhat like a judge that decides the result of a court case, of a trial, by flipping a coin. Let's say a fair coin. Okay? They're fair in the sense that they're not biased. They're not favoring one side over the other. But their answer has nothing to do with justice. So being unbiased is just one requirement, or one desideratum. Questions so far?
How do you represent the symmetry property?
Symmetry property.
Yes, you said before.
That it doesn't overshoot more than undershoots? That's the bias. So when you say it doesn't overshoot more than undershoot, that's not very well defined, because how do you measure overshooting and undershooting? You could say that the amount by which it overshoots, the maximum amount it can overshoot by should be the same as maximum amount it can undershoot by. That's a different criterion. The criterion we have here is that the average overshooting equals the average undershooting. It could be that when it undershoots very rarely, but when it does, it undershoots by a lot, and when it overshoots, it happens more often by a small amount. From our point of view, that's okay. They're balanced on average. So this is what is captured by the expectation. Another way of thinking about it is, this is our ideal criterion, right? That the expectation is the same as this, right? But you can write it equally well as the expectation of the error. The estimator minus the true value. You want this to be 0. Okay? This is the same as this, algebraically. It's the same thing. But here you think about, what I'm looking at is the amount of overshooting and the amount of undershooting. And I want the expected amount of overshooting to be, or undershooting to be 0. What's crucial here is that this is not raised to the squared. Right? This is without squaring. So overshooting and undershooting tend to cancel each other. If we squared it, then they will not cancel each other, and that would be the MSE. So you want the mean error to be 0, and the mean squared error to be as small as possible.
So I feel like the unbiased and fair aren't quite the same, because so from your earlier example, if you padded with one head and one tail, so it's number of heads plus 1 over total tosses plus 2. You're not favoring either, but you have introduced bias.
Yes, you have. That's very good. So what does it do when you pad with one head and one tail? You have 10 flips, but you pretended that you had 2 more, one of which landed on head and one of which landed on tail. What does it do to your answer? It doesn't bias it in terms of up or down. You're not biasing, as you said, towards head or tail. But it does change your answer on average. In what direction does it change it?
It biases it towards the 50-50?
Yes, it biases it towards the middle.
It's not necessarily 50-50 though.
Right, but it does push it towards the middle. Take it to the extreme. Pad it not with one head and one tail. Pad it with 100 heads and 100 tails. And you're still only allowed to flip 10 times. Now you're really bounded. Your answer is going to be right around 0.5. Right? Or if you pad it with only one head and one tail, you're pushed away from the extremes. You will never come up with the estimate of exactly 1 or exactly 0. All the answers are pushed towards the center. Which means you don't have to push only towards the center. If you think that for some reason you want to push the answer towards 0.3, then pad with 3 tails and 3 heads and 7 tails, or 30 heads and 70 tails. Introduce some padding, some initial pseudo counts in the proportion that you believe in, and then you allow the data to push you away from it, but you're kind of starting with a bias towards a certain answer. In many estimation problems, a good estimator is very easy to derive. It's something of the type of relative frequency, number of heads over number of tosses. In many other situations, a good estimator is not easy to find. Sometimes you know what you want, but just deriving the expression for it is hard. Sometimes you don't even know what to choose. Reduce the bias, reduce the variance, improve asymptotic behavior. There are many other properties of estimators that are important. For example, you can have 2 estimators that have the same variance and the same bias, but one of them, maybe I should be careful how I say it. They might have the same MSE, but one of them is more efficient with regard to how much it uses data. So for a fixed amount of data, one of them gets to the answer faster. You could say it makes more efficient use of the data. Okay. So we can start talking about Bayes. All this is true whether you are a Bayesian statistician or a non-Bayesian, also known as frequentist statistician. So I want to introduce you to the players in the Bayes game. Bayes statistics is not just a technique, it's a very deep philosophy. And debates in the statistical community about using Bayes methods or non-Bayes methods run very, very deep, both emotionally and philosophically. And these debates have been going on for a long, long time. At the heart of the Bayes way of looking at things is the following. At any one time, you have in your head your belief about the possible states of the world. Not only which states are possible, but which are more likely or more probable than others. And then you're exposed to data. And that data causes a change in your beliefs about the world. It updates your belief about the world. So the whole Bayes mechanism, Bayes framework can be thought of as a mechanism for updating your beliefs about the world in the face of data. Okay? I'll come back to it, but I just wanted to plant this in your head. So the first player is called the prior. Remember that the world we live in is the world of trying to find the true parameters, theta. Okay? There are other worlds in statistics, non-parametric statistics, but a very large part of statistics is called parametric statistics, and it's all about finding theta. And for our purposes, machine learning is like finding H, finding Nemo, finding the hypothesis we're interested in. So the prior is a function, a distribution function over all possible values of the parameters. Now we already have a problem with the way we've discussed things until now, because theta is red, and red we said is constant. So how can you have a distribution over a constant? This is where Bayesians and non-Bayesians fall apart. Non-Bayesians, also known as frequentists, think of parameters as fixed things. They're red, they're fixed. We may not know what they are, but God knows, and they're fixed. And maybe somebody else knows, and maybe they will tell us later, and maybe we'll find out later. But it's a fixed number. It does not change. Now, they can go ahead and prove things about some estimators being good for some values of theta and not being good if the values are different, or some estimators can be uniformly good no matter what the value of theta turns out to be. There are lots of things you can prove, but they are fixed. Bayesians take the red of theta and paint it green. Bayesians thinks of thetas as random variables. Not quite the same as the random variables based on the data, but think about them as God's random variables, or some kind of process that happened before that had a random variable, and maybe it settled on a particular value of theta, but before it settled, it had a distribution over all possible values of theta. Alternatively, the way of thinking about a prior is it just captures your prior beliefs about which values of theta are more likely than others. So let's stick with that interpretation, that it just captures theta is actually fixed, but we have a distribution that captures our belief about which values are more likely than others. Example, you have a coin and you want to know the probability of head. Before you flip it, we said that any value between 0 and 1 is valid. But realistically, how many of you have seen coins that have probability 1 of falling on head? Not very likely unless both sides are head, right? Realistically, you expect the value of probability of head to be somewhere around 0.5 for most coins. Maybe not exactly 0.5, maybe a little Gaussian centered at 0.5, but somewhere around 0.5. So you could use a distribution like a Gaussian to capture your prior belief about possible and likely values of theta. It could be a Gaussian between 0 and 1, or it could be, you could decide that no, you believe that every value is as likely as every other value, which means it will be a uniform distribution from 0 to 1. What you have in the x-axis here is theta, and on the y-axis you have phi of theta. And the area here has to sum to 1 in both cases, or it could be anything else. Now, if you know something about the factory that makes these coins, you may be able to put in a specific distribution. For example, you may know that every now and then the machines by mistake put head on both sides, and that happens with probability 2%. So you would put this little bump here on 0 and on 1 if it puts a head on both sides here, if it puts a tail on both sides here. And even though this is a continuous PDF, there would be 2 points that have real mass. You can do anything you want there, as long as it ends up being a bona fide distribution that sums to 1. So that's our prior. By the way, in the literature, statisticians like to use pi for a prior. So you'll see pi of theta. It's the same as p of theta. Now, I told you that theta and h are the same thing. Think of them interchangeably. So, suppose you have a prior on hypothesis. And suppose, for some hypothesis, the prior says they have a probability of 0. What does this correspond to in the terminology of machine learning? What does it mean to identify one or more hypotheses as having a prior of 0? Bias. Yes, what kind of bias? Somebody else. Hard bias. Prior of 0 is the same as hard bias. So what we did with our language bias or representation bias, when we defined the language and we said some hypotheses cannot be represented and therefore we are throwing them out, we're not considering them, can be thought of as imposing a prior that assigns 0 to all these hypotheses and non-zero to the others. Now when we assign non-zero to the others, how do we distribute the mass of 1 among all the others? If we distribute it uniformly, that's a uniform prior, and that means we don't have any soft bias. But if we don't distribute it uniformly, if we assign more of it to some than to others, that would be a form of soft bias. So P of h greater than 1 corresponds to possibly a soft bias. And if P of h1 equals P of h2 for all h1, h2 in the hypothesis space, this corresponds to a uniform bias, a uniform prior, right? Which means no soft bias, uniform prior. Uniform priors often go by the name uninformative priors. Uninformative because this is what you would use when you have no information and no reason to prefer one thing over another a priori. Some people might arguably call it a cop-out. Because if you say, well, I don't know what prior to choose, I'll just choose uniform, well, then you're choosing something. It corresponds to a very specific choice. Furthermore, it's not that well defined mathematically because often you can take a problem and reparameterize it. And when you reparameterize it, what used to be a uniform distribution in the original parameter space ends up being a non-uniform distribution in a different parameter space. So even the notion of being uniform in a space is not that well defined mathematically. It's defined only relative to a particular parameterization, and the parameterization is often arbitrary. Please.
Well, why can't we then define the prior as being uniform with respect to that particular parameterization, even if they undergo a transformation?
Yeah, you can. But that gives more fuel to the people who say you're doing something arbitrary. One of the most common kinds of debate between frequentists and Bayesians is frequentists tell the Bayesians, you know, everything you do depends on the prior, but how do you know which prior is right? To which the Bayesians would say, we don't know which prior is right. In that regard, Bayesian statistics is highly subjective. It's just a tool. In comes your prior, out comes the calculation. You put in a different prior, we'll give you another calculation. There's nothing in Bayesian statistics that tells you whether your prior is good or not. The prior is external to the calculation. You just plug in whatever you want. So the frequentists will say, you know, so you're arbitrary. You know, it's not guaranteed to be correct. And the Bayesian would say, you're right, it's not guaranteed to be correct. And the frequencist says, ha! But then the Bayesians say, wait, you're also using a prior. And the frequency says, no, I'm not. And then a good part of what Bayesians do with their time is go around looking at non-Bayesian papers and finding what the prior is, because often the prior is hidden there. For example, often it's uniform. It's just not showing in the formalism. But they show that the methods that the non-Bayesians use are in some sense equivalent to a Bayesian method with some prior. So then they go back to the non-Bayesians and tell them, you're doing Bayesian statistics, you're just not admitting it. You're using a prior. I mean, this is exactly the kind of arguments that you hear. You are using a prior, it's just not explicit. All we're doing is we're making the assumptions explicit. Well, you're not. And the battle goes on and on. There are some extreme cases. There are cases where no Bayesian estimator can be derived for a situation where a non-Bayesian estimator is easy to derive. But these are very extreme, unusual cases. Most cases you can take what a frequentist does and interpret it in a Bayesian way. Okay, so we have a prior and we have its relationship to machine learning concepts of bias. The second player, I'll just introduce it, we'll come back to it later, is called likelihood. Likelihood is the probability distribution. It's a conditional one. It's the probability of data conditioned on a particular value of the parameters. So you can write it as P of data given the parameter. Just like statisticians like to use pi for prior, they also like to use L for likelihood. So you will see likelihood of data given the parameters. But again, this is the same as this. It's probability function. Now if we stick with our original coloring scheme, I want to point out to you that these are two different beasts, a prior and a likelihood, in the sense that a prior is the distribution over parameters, and the likelihood is the distribution over data. Conditioned on parameters, but it's essentially a distribution over data. So this is, let's ignore this. This is probability over red, and this is probability over green. Given the value of red. The thing before the given is more important because that's the thing that has to sum to 1. The thing after the given, the conditioner, is a fixed constant. Now, how do we relate this to what we saw in machine learning? You can think of a likelihood as measuring the degree of agreement or consistency between the hypothesis and the data we saw. This is the hypothesis. We sometimes call it theta. I'm sorry, we call it H. This is also D given H, right? Degree of agreement between the hypothesis that we're currently assuming and the data we just observed. In the very first part of machine learning, that agreement we thought about in very crude binary terms, either consistent or not consistent. Right? So when we said that the data was inconsistent with the hypothesis, or equivalently that the hypothesis was inconsistent with the data, the way we can capture it with the likelihood is to say that the likelihood of the data given this hypothesis is 0. So when probability of particular data given a hypothesis is 0, this corresponds to D is inconsistent with H. Do you remember our version space and the candidate elimination algorithm when we start with a big version space, and as we get more data, we eliminate hypotheses that are inconsistent with it? This corresponds to starting with a parameter space, H, theta are the same thing, and as we get more data, getting rid of hypotheses that have a likelihood of 0, that give the data a likelihood of 0. This is a crude and extreme thing to do. In addition to getting rid of hypotheses that give the data that you saw a likelihood of 0, you can also penalize hypotheses that give the data a low likelihood. Whereas we didn't do that with our version space. With our version spaces, it was either you're consistent or you're not consistent. So Bayesian statistics allows you to introduce shades of gray to what was before just black and white. And it was black and white and along two dimensions. First is a priori, before you saw the data. That's the prior. Either you, in our original formulation, you either threw it out through hard bias or you didn't. Now we're using the soft bias. We're introducing gradations. And the second dimension is when you see data, do you only use it to rule out hypotheses that are inconsistent, namely that they have a likelihood of 0 of producing the data, or do you also use it to penalize and re-rank, reorder hypotheses based on how much they agree with the data? So the agreement with the data is no longer 0, 1. It could be more or less. Prior and likelihood. These are the two main players. I have to let you go. We'll continue next time.